Welcome to the second unit in this week. Recall that in Unit 1, science was defined in three main ways. It was defined as a body of knowledge, a method for acquiring knowledge, and as an institution. In this unit, therefore, that method of acquiring scientific knowledge, known as scientific method, will be discussed in detail. The emphasis will be on how it works in real life and how it has worked in science. Also, the method of effective thinking that you will learn in this unit will be of great value to you if you apply it to solving life problems. At the end of this unit, therefore, you should be able to 1. List sequentially the steps of scientific method. 2. Explain vividly with one example how the method can be used to solve a named life problem. 3. Explain vividly with one example how the method can be used to solve a hypothetical scientific problem. 4. Assess clearly the use of the steps of creative and critical thinking when given a hypothetical case story. Superficially, science is a collection of facts, that is, body of knowledge, that describes and explains the workings of nature. Although these facts are interesting, even fascinating, they are not the essence of science. Rather, the excitement of science lies in the intriguing observation and the carefully designed experiments that scientists have designed to help us learn about nature. The important thing here is the process of science, not just knowing the fact, but appreciating how scientists discover and continue to discover those facts. The process is characterized by a sequence of steps which enable scientists to approach objective truth as closely as possible. Taken singly, most of the steps are commonplace procedures carried out by people on a daily basis. But taken collectively, they amount to one of the most powerful tools man has devised to know and control nature. What are the steps of science? The first step of science is observation. Observation comes from noticing resemblances and reoccurrences in the events that happen around us. Observation is therefore the first step of scientific method. Thus, anything that cannot be observed cannot be investigated by science. For example, a young student observes that maize grains, which were placed in a wet container inside a dark cupboard, germinated, but that the leaves were pale yellow instead of the normal green color of leaves. Scientific observation can be both direct and indirect. Direct observations are made with the aid of senses, just as the hypothetical student observed the maize grains with his eyes. Indirect observations are performed with the aid of instruments. Atomic nuclei or magnetism, for example, cannot be perceived directly through our senses, but their effects can be observed with instruments. What other things do you think can be observed indirectly? So, observations can also be classified into spontaneous or passive observations, which are unexpected, induced or active observations, which are deliberately looked out for. Effective spontaneous observation involves firstly noticing some event or object. The thing noticed will only have meaning if the mind of the observer, either consciously or unconsciously, relates it to some relevant knowledge or past experiences. It can also be important if the observer, in the process of thinking over it, arrives at some hypothesis. From our hypothetical example, the student noticed that the pale yellow color of the leaves of the maize grain were different from the normal green color of maize grains. He thus related what he observed with his previous knowledge. Powers of observation can be developed by cultivating the habit of watching things with an active, inquiring mind. It is no exaggeration to say that well-developed habits of observation are more important in scientific research or even in our daily living than a large accumulation of academic learning. Correct observation is a most difficult art, acquired only after a long period of errors and experience. The difficulty lies largely in our unsuspected bias. People forever see what they want to see or what they think they ought to see. It is extremely hard to rid oneself of such unconscious prejudice and to see just what is actually there, no more, no less. This is the reason why a scientific observation must be repeatable. Science does not take any observation at face value. Several scientists must be able to repeat that observation independently and report the same thing for that observation to be of value to science. After an observation has been made, the second step of the scientific method is to define the problem. Problem definition. In this step, questions are asked about the observation. If the hypothetical student in our previous example shows further curiosity, he will decide to find out why those seedlings had pale yellow leaves instead of green. This is therefore the definition of problem. He asks himself, why are the leaves pale yellow instead of green? This is the kind of casual question that the scientific method deals with. Science is therefore fundamentally about finding answers to questions. Significantly, not everyone sees that there may actually be connection with an observation. For thousands of years, even curious people simply took it for granted that any unsupported object that is thrown up in the air must fall to the ground. It took a genius, Isaac Newton, to ask, how come? And few questions have ever contributed more to science as this. Good questioning, like good observation, is therefore a high art. To be of value to science, a question must be relevant and it must be testable. Experience helps in deciding if a question is relevant or not. To find answers to scientific questions, scientists use past experience, ideas, and observations. Hypothesis testing. This is the third step of scientific method. Do you know that this involves the seemingly quite unscientific procedure of guessing? One guesses what the answer to the question might be. Scientists call this assumed answer hypothesis. A given question, as you might be aware, may have thousands of possible answers, but only one right answer. Thus, there are excellent chances that a random guess will be wrong. The scientist will only know if his guess was correct after he must have completed the fourth step of scientific method, which is experimentation. The main function of a hypothesis, therefore, is to predict new experiments or new observations. Thus, our hypothetical student in previous examples will try to state all the possible explanations of his observation or all the possible solutions to the problem he defined. One possible explanation he might give is that the pale yellow color referred to is the characteristics of the particular variety of maize that was germinating in the dark cupboard. Another explanation he might give is that the pale yellow coloration resulted from exclusion of light. As we noted before, all the hypotheses relating to a problem cannot be valid, and the only way to decide which hypothesis is valid is to test each of the hypotheses. If experimentation shows that the first guess was wrong, scientists then must formulate a new hypothesis and once more test for validity by performing new experiments. Clearly, the guessing and guess testing might go on for years, and a right answer might never be found. Obviously, much faster progress would be made if the number of hypotheses were few. The amount of previous knowledge or experience a scientist has enables him to achieve this. This shows us the importance of knowledge for scientific progress and the truly social character of knowledge. It is while hypothesizing that common sense, intuition, and lucky accidents help science enormously. It is therefore good to hypothesize that common sense, intuition, and lucky accidents help science enormously. The story has it that in one famous case, the German chemist Kukule went to bed one night after a fairly alcoholic party. In his sleep, he dreamt of 6 monkeys chasing one another in a circle, and the tail of one held in the teeth of the other. Practically, our whole chemical industry is based on that dream because it told the sleeping scientists what the structure of benzene was. Scientists at that time had been trying to figure out the structure of benzene. Kukule then concluded that benzene has 6 carbon atoms chasing one another in a circle. And that is exactly the present structure of benzene. And it is good to know that benzene is the fundamental parent substance for thousands of chemical products. Since it is the function of every experiment to test the validity of scientific guess, the 4th step of scientific method is experimentation. You might be aware by now that answers without evidence are fully unsupported opinion. Experimentation can provide the necessary evidence, and anyone who experiments after guessing at answers becomes truly scientific in his or her approach. Experimentation is by far the hardest part of scientific method. There are no rules to follow. Each experiment is a case unto itself. Technically, knowledge and experience usually help. Making a correct decision on the means by which a hypothesis might best be tested shows the difference between a genius and an amateur. Can you think of how the young student in our hypothetical example would gather evidence in order to refute or confirm his hypothesis? Let us examine the 2 hypotheses regarding the young man's observations of pale yellowing leaves of maize seedlings. The first hypothesis to explain the observation was that the yellowing was due to the variety of maize germinating. A simple way to test that hypothesis is to collect various varieties of maize, put them in the dark cupboard, and observe the result. All the varieties will be found to have produced the same pale yellow leaves. The other hypothesis, which states that exclusion of light produces the pale yellow leaf effect, can easily be tested. This is done by germinating a batch of seed in the dark and another batch in a well-lit condition. The well-lit condition serves as the control. It provides a standard of reference for assessing the results of the experimental series. It will be found that the seedlings in the dark will be pale yellow, while those in a well-lit condition will have the normal green color. What do you think gives the green color its plant? The next step after experimentation is conclusion. The test of the first hypothesis, therefore, leads us to reject that hypothesis while our test of the second hypothesis leads us to accept the second or alternative hypothesis. Thus, our respective conclusions are: yellowing of the leaves was not due to the variety of maize germinating. Exclusion of light caused the yellowing of the leaves. Scientific conclusions can be redefined, modified, and clarified when the situation arises. Some other conclusions may even be overthrown or discarded. For instance, the young man who observed the pale yellow leaves of maize seedling may want to find out if the same result will be obtained with seedlings of other plants. He may also observe that in a large maize farm, some rare seedlings which lack green pigment may exist. This will lead him to modify his original conclusion. He may add that other factors besides lack of light may cause yellowing of leaves. Let us look at theory, which is the next step of scientific method. What is a theory? Would you be able to attempt an answer? If you cannot, okay, let us attempt one together. A scientific theory is an explanation about the cause or causes of a broad range of related phenomena. It differs from a scientific hypothesis in its breadth of application. A theory is usually proposed when a hypothesis has been supported by really convincing evidence. This evidence must be obtainable in many different laboratories and by many independent researchers. Theories are open to test, revision, and tentative acceptance or rejection. As soon as new information is observed in the course of applying the theory, such existing or established theory is revised. Thus, a new theory emerges to replace the existing one. This is a guarantee for the development of science and human knowledge. Theory formulation, therefore, leads to the advent of various scientific theories. To help in the organization, a working hypothesis is usually required. Thus, theories start as hypotheses or tentative formulations meant to explain the phenomenon under investigation. When a hypothesis is confirmed through experimentation, it becomes a theory. Theories take various forms, which may be as a diagram, equation, statistical, and propositional formulations. Every good theory, however, must have good predictive value. It prophesies certain results. Scientific prophecies always have a considerate amount of evidence to back them up. Additionally, a scientific prophecy does not say that something will certainly happen. It only says that something is likely to happen, and with a stated degree of probability. Theories that have proved to be universally valid and have a high degree of probability are called natural laws. Theories, therefore, enable us to explain, predict, and control phenomena. They also provide us with a new way of looking at a familiar object or phenomenon. The theory of optics, for instance, provides us with a new way of looking at the phenomenon of light. Before this theory was discovered, people thought of light in the form of patches, shades of color, etc. With the theory of optics, people's way of looking at light changed. Light is now viewed as traveling, and this gives room for explaining a wider range of phenomena than the old way of looking at light. Since the advent of modern science in the 16th and 17th centuries AD, many scientific theories have been proposed. These include the theory of universal gravitation, the theory of evolution by natural selection, atomic theory, genetic theory, relativity theory, quantum cosmological theory, the Big Bang theory, theory of falsifiability, etc. We have just gone through the processes of scientific method. How do you think it works in real life? Let's suppose that you wake up one night with a skin rash, which is, we could look at it as an observation. You want to know what caused this rash. This is casual question.
Hello.
You first try to figure out how the situation is similar to other known situations. Perhaps a classmate of yours had a similar rash that was caused by an allergy to the grass at a close-by football field. You realized that your rash has appeared after all the football games that you have played on that field. The similarity between your friend's allergy and your rash leads to the explanation or hypothesis that your rash is caused by an allergy to the grass too. When you play football on several other fields, all with different kinds of grass than your nearby football field, you do not get such a rash. If your hypothesis is correct, you would not expect to get a rash from other kinds of grass. So this time around, you're making prediction. So when you play football on several other fields, all with different kinds of grass than your nearby football field, that is a process of experimentation, you do not get a rash looking at the result now. Your result should match the prediction of the grass allergy hypothesis, from which you decide that your rash is caused by the grass at a nearby football field. This forms your conclusion. However, if this was your only hypothesis, you have not actually identified the cause. Perhaps your rash was caused by fertilizers, pesticides, bacteria, fungi, or other agents associated with the grass or soil at one football field and not the other. By testing a single hypothesis, you have not ruled out any of these other possibilities. To do so, you will have to devise alternative hypotheses, make predictions from them, and obtain experimental results to compare with the prediction. By this process, you may be able to reject some but not all of the alternatives, or you may be able to hypothesize even the green allergy hypothesis. Either way, you make progress by testing several hypotheses, not just one. If you can reject all, with the exception of the grass allergy hypothesis, you can more confidently conclude that the grass caused your rash. Furthermore, you may decide not to play in that particular field again so that you can avoid the irritating plant. You may agree with me that all of this seems like common sense, which it is. The use of scientific method is not restricted to scientists. A principal characteristic of scientific thinking is that the sequence of observing, hypothesizing, experimenting, concluding, and interpreting is a cycle with new ideas produced at every step. To the curious scientific person, a conclusion or a theory is never the final answer. There is always something more to study, something new to learn. So, can you be that person? In addition, we live in a complex but rapidly changing society in which we have to make simple or difficult decisions every minute of our lives. Such decisions might be vital to both our health or that of other people, as well as their success and happiness. How well the decision turned out to be will depend in part on the procedures of the thinking pattern we use. The importance of the scientific method of thinking is richly illustrated by the history of science. Until 17th century, science progressed quite slowly. However, in the last 3 centuries, procedures of thinking, the scientific method which we have just discussed, evolved. Its use has been responsible to a large extent for the impressive success of modern science in discovering the secrets of the universe, as well as in developing solutions to technological problems. Many of our most serious problems can be lessened or even solved by the application of these techniques. Progress in solving most human problems has lagged far behind progress in science. Most human problems cannot, of course, be taken to the laboratory to be worked on, and some aspects of scientific method may not apply to these problems. However, a large body of evidence confirms that effective method of thinking can be of great value in solving everyday humans' problems. The procedures of science, which you have learned, require 2 distinctive different types of thinking. They are creative thinking and critical thinking. Creative thinking may be defined as a formation of possible solutions to a problem or possible explanation of a phenomenon. Critical thinking, on the other hand, is the testing and evaluation of these proposed solutions. Effective thinking is both creative and critical. Indeed, both kinds are essential in all areas of human activity. In diagnosing an illness, for example, a physician first develops possible diagnoses that seem to fit the symptoms. He then evaluates them by further examination of the patient or by laboratory tests. The final diagnosis cannot be right unless the possible diagnoses include the right one. Even when the possible diagnoses do include the right one, the physician may still make a mistake by being careless in criticizing them or settling on the wrong path. So, if you have understood the scientific method, you would agree that it is both creative and critical. Outside the laboratory, however, both scientists and laypersons tend to be a bit careless about both creative and critical aspects of thinking. When our feelings are aroused, we are likely to act first and think only after it is too late. Thus, to create and criticize are the twin watchdogs of the effective thinker. The general process of applying creative and critical thinking to problems can be described as a cycle of 6 phases. This cycle should not be treated as a rigid procedure in which each phase must be completed before the next one began. In practice, you may go back on an earlier phase or work on several phases at the same time. But if you are to have any real assurance that your final decision is sound, all phases must be completed. So, why don't you begin now to practice using this cycle? You should know that every phase of decision making is strongly affected by the fact that each one of us sees both the world and ourselves from our own personal point of view. This can interfere with objectivity, which is important to effective thinking. How effective our thinking is depends partly on how objective we are in viewing ourselves and the world without bias. However, absolute objectivity is impossible because we observe the world only through the lens of our own point of view. You should keep in mind 2 essential things for objectivity. The first is to concentrate on the pursuit of truth in all the problems you take up, no matter how unpleasant or threatening it may be. Science has a system of punishing failures of objectivity. But in human settings, you must develop your own sense of discipline. The second element in objectivity is to be open to your feelings. Exclude them when they are not relevant and include them when they are, and you must be able to discern the difference. It should now be clear to you that perfection in thinking cannot be attained. Effectiveness is the important thing. Also, a satisfactory solution to every problem is too much to expect. The person who expects to solve every problem and make the right decision every time is unrealistic. Effective thinking, like playing a musical instrument, requires practice. This is important both for understanding the techniques fully and for developing skills in applying them. So, what stops you from practicing now? A scientific theory is an explanation about the cause or causes of a broad range of related phenomena. A theory explains how things are related or their common properties. Theories take various forms, which may be as a diagram, equation, statistical, and propositional formulation. For your exercise, please go through the exercise section. Let us wrap up this unit. In this unit, we learned that scientific theory is an explanation about the cause or causes of a broad range of related phenomena. A theory explains how things are related or their common properties. Theories take various forms, which may be as a diagram, equation, statistical, and propositional formulation. What were the steps? Steps of scientific methods identified were observation, problem definition, hypothesis formulation, experimentation, conclusion, theory formulation. For observation, we learned that it can be direct or indirect, spontaneous or induced, etc. Scientific observation must therefore be repeatable. For problem definition, it involves question asking about the observation made. Scientific question must be relevant and testable. Hypothesis formulation, however, involves guessing or proposing answers to the questions posed. In experimentation, we learned that answers without evidence are unsupported opinions. Thus, experimentation provides the necessary evidence for accepting or rejecting the proposed answer. Conclusion can be defined, modified, and clarified when the situation arises. Theory formulation will therefore form the main topic of discussion in our subsequent unit. We also learned that scientific method is both creative and critical. Thus, it can be used to develop effective thinking, which is very necessary for solving scientific and real-life problems.